Welcome to lesson 18 of this Arduino C++ course, and today we're going to concentrate on project design. Now, in previous lessons we've looked at the code and various sensors, buttons, even the LCD screen. Today I'm going to work through a project. The project we're going to build is a railway speedometer. In other words, I want to measure the speed of a model railway train between 2 points. That's going to be the project, and I'm going to show you how I went about designing this project, because this has implications for any project that you want to build. Now, obviously, if you don't want to learn how to design your own projects and just want to copy the code for this one, then I suggest that you skip towards the end of the video and just download the code for Speedometer version 3. And the code for that, as always, is available on the Digital Town website. The link is below the video and is actually in the bottom left of this screen. Going over to that website, go down to lesson 18, you can click to download the code. I have the circuit diagram available. Clicking on the circuit diagram will bring up a larger version that is easier to work from. Anyway, let's have a look at the workbench to see the finished project. So this is the project as I've built it up. As you can see, we've got the LCD screen. I press the button to arm the system, and then I have a piece of wood for my simulated train, and as the train moves past the sensors, you can see that I get a speed readout in O, OO, HO and N gauge. Now this is to do with the different scales of model railways. Depending on the scale, of course, the speed is different. Now what is interesting about this project is I finished up using these IR sensors, and they were the one sensor that I did not think I would use. So I'm going to show you why I finished up using them. So this project was something that someone had asked me to build, and I'll be honest, when I tend to think about timing between 2 points, the ideal system for me would be a beam that goes across the track. This is my track here, and the idea is that the train would break the beam. I would then have a second beam further down the track, and that beam would then be broken. That would be a very, very exact method of, if you like, timing between 2 points. Now, to do a project like that, I assumed that I would finish up using something like this. This is a little laser sensor module. Let's just see if I can get it into the camera. So that fires a little laser beam, and then we have this module that basically has a receiver. You fire the laser beam at this little receiver unit, and it's one of those cases, it's a digital switch. It is either being hit by the beam or it is not being hit by the beam. Therefore it gives a 0 or a 1. Now, going over to the Arduino IDE, I've just written analog read, as we would write it, for pin A0, and digital read for pin 8. Now, the difference between an analog read and a digital read is a digital read is much, much faster. So I can do 10,000 analog reads per second, or I can do 200,000 digital reads per second. Now, if we think of the image, that means that, if you like, the number of times that I can check if the beam has been broken is 20 times more than I can check this reflection. The other thing, with a digital system, I could actually use an interrupt to make this even more exact. So my initial thoughts were break the beam. However, the problem with breaking a beam is it means that I have to have a transmitter on one side of the track and a receiver on the other side of the track, which means I've got to have wires going under the track or over the track. Now for this project I only wanted something temporary and something I just put in place rather than something fixed, so that would be a bit of a pain if I'd got across the track. So I decided to do some tests with the IR system, this reflection. Now what I was concerned about is obviously it sends a beam out. As the train comes by, it reflects that beam back to the receiver unit. However, the beam doesn't go out in a straight line, it will sort of form a cone. So my concern was if I got light going out sort of to the left or to the right, I could get weird reflections coming back into the receiver. So if you're building a project like this, sometimes it's quite useful to do some tests. And I'm going to show you how I tested these units. So the sketch I'm going to use is just a test sketch. Basically I'm checking that everything is working. We've got the button with a 4.5 to 10k pull down resistor. I've got the right IR button pin is A1 and the left IR unit is on A0. I've got the liquid crystal display attached using the wire library, which we did in lesson 17, so I'm not going to go through all the details again. Then I have started the serial monitor, set my pin mode, set up the LCD screen, and all I'm saying is on line, top left, write hello world, because that just tells me that the screen is working. And then in the main loop I'm just going to serial print the button state, the left IR sensor and the right IR sensor. So let's get that uploaded. So now that everything is uploaded, as you can see we've got hello world, so we know the screen's working. Press the button goes to 1. Block the right IR sensor, we can see the value drop to 33, and if I block the left one it's dropping down to 41, something like that. Obviously you can adjust that value by adjusting the potentiometer on the top of the board to set the sensitivity. But at this point I now know that everything is working, and this then allowed me to do some testing. So for the testing, what I'm going to do is basically blue tack my vernier calipers to the workbench, then use this piece of wood as a simulated train, and I'm going to see at what accuracy the IR sensor triggers. So my testing basically consists of having the vernier blue tack to the bench and then pushing along with my simulated train until all of a sudden the sensor changes. Now that has changed at sort of 15 millimeters. If I push it back again and try again, there we go, and this time it's at 15.6. Now obviously I'm doing it quite roughly at the moment. However, when I completed my own tests, I discovered after numerous tests that I could get the reading to be within about 0.5 of a millimeter. The other thing that I discovered was that at the moment I have the sensor in this orientation. If I placed it in an upright orientation, I found out that it was even more accurate, and I was getting to about 0.3 of a millimeter. Now obviously this varies depending how far away you are from the object that is moving by, because obviously the light will come out in a bigger cone. But if you're keeping it within 20-30 millimeters, you are going to be fine down to an accuracy of about 0.6 of a millimeter, being a pessimist. Now I then started to do a little bit of mathematics just to try and work out the number of milliseconds per millimeter that would equate to 1 mile an hour. Now the reason for doing this is when you build a project, it's very easy to say I want it totally accurate. Well, if you want super accurate, you're going to buy some very expensive sensors and, you know, very complicated things. It's a bit like if you want to know the voltage of something, do you need to know the voltage to within 1 volt, within 0.1 of a volt, 0.01 of a volt, or 0.001 of a volt? Depending how accurate you want to know that value will make a great difference to the sensors that you are using. And so for this model railway project, I decided that I needed to apply a little bit of sanity, and I did a little bit of maths, and I found out I work in 7mm scale, which means that 1 mile an hour is the equivalent of 10.26 millimeters per second. Now that means that if I have an error of half a millimeter in my, if you like, my receiver, that's going to give me an error of around 0.2 of a scale mile per hour. I can live with that. This is a model train. This is not doing anything super accurate, because even the speedometer in my car, I think, has an error of something like 10% or something. And again, that error varies depending if I've got new tires on or worn tires. So I did some sort of different calculations to work out what the problems would be. And I discovered that with using these sensors, the error was within an acceptable amount, and therefore they were usable. Now, up till now, I've talked about the accuracy of the sensors, but when you're building a project for real, there's something else that you need to think about, and that is your ability to physically build the project accurately. So let's go back to the breadboard and I'll show you what I mean. So looking at my sensors, I have set my sensors 100 millimeters apart. Now, when I say 100 millimeters, that is 100 millimeters from the edge of that board to the edge of this board. Now obviously if you put the sensor in the opposite plane, you can do this a little bit more accurately. Now, because of the way these are plugged into the breadboard, it's not exactly 100 millimeters, but it's close enough. But it starts to show some of the problems when it comes to the physical build. Now, if I was building this project, I would use a 3D mounted enclosure. So let's just show you what I mean by that. So this is the software that I use for designing my 3D stuff. And what I would do is mount the sensor in here. So if you like, the sensor was clipped in between these two pegs here. Now, obviously, because I'm doing this on a 3D printer, I can get the distances now between those points to be extremely accurate. However, if you're doing it by hand, so going back to the webcam, let's imagine that you don't have a 3D printer, so you're going to use a piece of wood and you're going to cut a slot in it with a saw. You come down to that bit of how accurate can you make that slot, but also when you've put the two slots in, going back to our code, how accurate can you put those slots apart? Now, with my carpentry skills, that's why I have to have a 3D printer, my carpentry skills are so bad, I would guarantee that I'm going to be 1 to 2 millimeters out. Now obviously I can change this variable and that will then sort out all the calculations to take into account that, you know, the slots are at the wrong position. However, I've got to cut those slots. Let's say I do them at 102 millimeters apart instead of 100, but is that 102 millimeters or is that 102.2 millimeters? Again, it's that bit, how accurately can you measure something? So in this case, I realized, going back to my diagram, that the variation that I was going to get off the IR beam did not really impact the accuracy as much as the, if you like, the build of the project did, and if you like, the accuracy of this was within the tolerances that were fine for this particular project. Now this is important because very often when I see beginners trying to build a project, what they are interested in obviously is the most accurate sensor. But obviously if you cannot mount that sensor to the accuracy that, if you like, the sensor can read at, then you may as well have a cheaper, less accurate sensor, save yourself some money, and your project is going to still come out with the same accuracy at the end of the day. So this is why, if you like, in this project I finished up using some sensors that I didn't expect to use, purely because when I did my testing I realized that they were more than adequate to do the job. So now that I have chosen my sensors, let's have a quick look at the code of how this works. Now, as in the previous sketch, we've got the left pin, the right pin, and the button pin. Current millis is back for the timing, and it is being used for the debounce on the button. I then have an array of unsigned longs. Now that's because we're going to take the time that the beam is broken. Now coming back to my picture here, obviously I've got a beam and, well, now we're using these sensors. Imagine we've got these two sensors, the train is coming in this direction. I need to be able to time from when this beam is broken to this beam is broken, or if you like, to when they now reflect. But also the way I've built the project, I want it to work if the train is coming in the other direction without resetting any code anywhere. So because of that, I'm going to have an array that stores the time in milliseconds that both beams started to be triggered. I've got a sensitivity value. That is the value that if I'm going to say that the beam has been reflected. Now in my tests I was seeing reflection values sort of below 40 most of the time, 45 I think on the left one at times. So I'm going to give a value of 50. If the value is below 50, I'm assuming that there is something blocking the beam. I've got a variable here, speed mode. This is going to keep track of the system and show it where it is, if you like. And then we've got another unsigned long, which is the train time. We've got a variable for the millimeters between sensors. So if you're building this project and you want it over a longer distance, shorter distance, the longer the better, but over 100 millimeters is more than adequate for the accuracy. And I've left some of my figures in here. If you are interested, please check them. If I've made any errors, let me know and I'll update the sketch accordingly. Right, I've then, from these calculations, I came up with some variables, and these variables are used later on as constants to if you like, turn the true millimeters per second into the scale millimeters per second. Coming down to the setup, very, very simple. Start the serial monitor, pin mode for the button. For the LCD screen, just like in lesson 17, I'm setting the cursor top left, and that's going to be for O gauge, which I've got as, I think, 140, where is the scale? 7 millimeters to the foot. You can work that one out yourself. The scales, I've then got OO and HO. OO is 4 millimeters to the foot. HO is 3.5, and then I've got N gauge, which I believe I'd listed as 2 millimeters to the foot. Right, let's come down now to the main loop and see what is going on. So obviously the code from the previous sketch is still here. That was just left doing its serial print. When you build the projects for real, you need to comment out your serial print statements. Now the reason for that is these take time. And when we're trying to do timings, the last thing you want is, if you like, a delay in your code caused by serial print statements. So we're going to start as always with current millis, taking the current time in milliseconds at the beginning of the loop, and then we're going to do a basically a button debounce to see when the button has been pressed. Now when the button has been pressed, obviously it resets the debounce, but that, if you like, is the trigger for the system. At that point, we're going to set the mode to 1. You'll see why in a moment. And those IR times in the array, those are the times when the beams were triggered. Both are set to 0. So everything is reset at the beginning as soon as the button is pressed. If you like, the button is the arming system. I've then got a switch statement. Now case 1 is in there. We've got a case 2 and a default. So the default is do nothing, and before anything is pressed, the system is running through the default. So when it gets to the switch statement, it doesn't do anything. As soon as the button is pressed, the speed mode, here we go, the button's pressed, and we go to mode 1. So in mode 1, if the one IR sensor is small, has no value, only if it has no value, okay, because all I want is the very first value when it's triggered. So it's only going to do an analog read on the left pin if it hasn't got a value in this array. Now the reason for this, if you remember earlier on, I was saying that we can only do, was it 10,000 reads per second, which means if I'm doing 2 reads, I can only do 5,000 reads of both per second. So as soon as the one has been triggered, I'm going to stop reading it. That way I can read the other one more accurately. Hope that one makes sense. So if the one sensor has been triggered, has no value, we're going to be analog reading the left pin, and the same for the other value. For that one, we're going to be reading the right pin, and it doesn't matter in our code which one gets triggered first. It's just, it will save the value and then just keep checking the other pin and the other sensor until it has been triggered. Now, once both of them have a value, so now both of them has been triggered, the trainer has, if you like, triggered both beams. At that point, we're going to move on to speed mode 2. So in mode 2, and we're still in our main loop, we're going round and round. When it comes round the main loop the next time, it's not going to go through the default, it's not going to go through reading the analog pins. Instead, it's going to come into here, and all it's going to do is work out, firstly, what is the difference in time between the beams being triggered. Now obviously it could have gone left to right or right to left, so we've got to work out which way round it was going. So we want, if you like, the largest value to subtract the smaller value. So if 0 is greater, if you like, the first element is greater than the second element of the array, the train time is IR times 0 minus IR times 1. Obviously, if the train was going the other direction, it would be the other way round. And once I'm done that, I'm going to serial print out that time in milliseconds. At this point, I don't have to worry about doing a serial print because I've taken my timings. I've got plenty of time now to carry on. And then we're going to reset the speed mode to 0. So it's all ready to go again next time the button is pressed. And we're also going to calculate the speeds in a function. Now the reason for doing all the speed calculation as a function was just to keep everything separate, and also it means if I made any mistakes, it's going to be in this one area. Now the calculations are quite simple. we've got the distance between the sensors multiplied by the constant for each scale, and we divide that by the train time, if you like, the time that it took to go between the two beams. Very simple calculation. Again, if I made any mistakes in my mathematics, please let me know and I'll add an extra sketch in there. Once I've got all of those values, all I did was serial print them out just to make sure that they all seemed sane. And once I'd got all of those sorted out, then it was just a case of doing just as we did in lesson 17 with the LCD screen, and I printed out the various speeds to the screen. And that is about it. So let's get it uploaded. So the sketch is uploaded, and if I move my simulated train, as you can see, nothing happens. Now that's because the system hasn't been armed, so we need to press the button. Now the system has been armed. As I move my simulated train across, we can see that we get a speed. If I reset it and go again, we can see that it goes a little bit faster that time, and I can do the same moving it in the opposite direction. So at that point, if you like, the proof of concept works. Now what I wanted to do was tidy up the code so that it just looked a little bit more presentable. So sketch 3 is absolutely identical. Coming down to the setup, everything is identical. It's when we start to get to the main loop, there are a few changes. This time, when I press the button, not only does it reset the timers and the speed mode, but it also puts a 0 in for all the speeds, because that way I know that, if you like, the button has been triggered, because before, when I pressed the button, the old values remained in place. The other bit that I changed was when it came down to the speed calculations. Do you remember, if you did lesson 17, you'll remember that I did a function for string padding, and I have used that string padding function again. This time it is passing a 3, that's going to be the length of the string. The pad is going to be a space, and then it is passing over the speed string. It's doing that for each of the different scales, but it just means that the final output on the screen will look a little bit better. So let's just get that uploaded and I'll show you what I mean. So this time, when I press the button, instead of seeing nothing happen, I get those zeros to tell me that the system is armed. I can then move the unit across and get a value. Again, press to reset, go back the other way, and I get my speeds. And you can see, obviously, O gauge, I'm doing an equivalent of 32 miles per hour. N gauge, I was doing 112 miles an hour. Now, going back to the code, for those of you who do not live in the UK or the States, for those of you who use kilometers per hour, I did actually put a conversion in for, basically there's 1.6 kilometers in a mile. So if you comment these lines out and uncomment these lines, you will get your speedometer working in scale kilometers per hour rather than miles per hour. So for those of you that are model railway fans, obviously this is a way to build a speedometer for those who want to sort of speed match their locos. But for those who are just building projects in general, I hope today's been helpful in understanding how, although this particular sensor would have been more accurate than this sensor, because of the limitations in, if you like, my ability to build physically the project and various other limitations, the final, if you like, result makes no difference to the output unless I'm going to start trying to measure the speeds of these trains down to sort of 0.01 of a mile an hour, which I can tell you for model railways is just not needed. So again, it's that understanding that the accuracy of the sensor doesn't need to be the best if you cannot build the project physically to the standard required. So that's it for today's lesson. Apologies again for my voice. I'm still suffering a bit from the dreaded lurgy. I am getting better. And if you want to help the channel, please click the like and subscribe. And again, this was a requested project. If you've got any projects that you want or any components that you want me to have a look at, just let me know, probably best through the Digital Town site. Just email me so that I can have a look at them, and I'll see what I can do. There are some projects that people have asked for that I will work through as soon as possible. So that's it for today. Thanks for listening, and I'll see you in the next video. Bye for now.